Hello there. My name is Michael Rundström. I work at Lund University as university lecturer in GIS and remote sensing. And welcome to this lecture about passive remote sensing data formats, georeferencing, radiometric correction, and resampling. Now, you should know already how the raster structure looks like, that we have a matrice that's built up by a number of columns and a number of rows. And this produces then different pixels, or as we call it in GIS, cells. But in remote sensing, we call them pixels, which are then picture elements. We have an X resolution and a Y resolution to the pixels that can be the same. That would mean a square pixel, but they can also be different. So you can have, for instance, 30 meters in X resolution and 80 meter in Y resolution. That happens. And passive remote sensing data are stored as raster data and built up by this type of matrice where we have columns and rows, and inside those we then have the different pixels. And the pixel is then have a certificate or a certain value that is related to the energy that has been reflected in that area on the ground. Now, for a satellite image to be possible to work with in a GIS, it has to have a geocoding as well. We have to know where this raster file or raster data is positioned on the Earth. And there are different ways to give that position. And normally, as the raster matrice is a very structured way of storing data, it is actually available to have a geocoding with only providing one coordinate somewhere in the data set. It's a bit different for different formats. For instance, Idrisi files, they want to have the minimum X coordinate and the maximum X coordinate, the minimum Y coordinate and the maximum Y coordinate. And also the spatial cell resolution, and then sort of a test that it works correctly is made, so that the X mean plus the amount of columns, and then each pixel or cell resolution should then be the same as the X max. Other formats that are used are, for instance, a TIFF image, and then actually the coordinate for the center of the upper left cell is provided in some way. If it's a TIFF file with an accompanying TIFF world file that we see here, this is a world file that you can actually look at in Notepad or some text editor. There we have the information for the GIS to correctly put the raster in position. We have the X coordinate, the X resolution of the pixel. We don't have any, these are rotation parameters, but it's not rotated in this case. And the Y coordinate, as the Y is actually going from the top to the bottom, that will be a negative Y. And then we have the coordinate of the center of the upper left cell. We can see that if the cell resolution is 1000, this X mean is actually at 1120,000, but as it wants the center point of the cell, it will be added by 500. So 1120, 500 is the x coordinate for this one, and 67, 14, 500 for this point. Sorry. So we need to have some geocoding in some way, and different formats have different geocoding. So the TIFF file needs a TIFF world file, accompanying file, a separate file with the same file name, but with a different extension of the file. And that's where the georeferencing information is stored. A satellite image can also be stored as JPEG, and then the same format can be available then as the JPEG world file, having the georeferencing information. There are also other formats that can be used. The GeoTIFF will have the georeferencing stored inside the image file, for instance. There can be an IMG, an image file format. It could be a grid, SRIS raster format, which is then a folder containing files that builds up the raster images. It could be maybe a ASCII grid file. That's a readable text file that contains the raster values or raster numbers, and you can see them. And that one also contains then the number of columns and rows and cell resolution. Often passive satellite data are taken in a multispectral form. That means we separate. There is one image that has recorded the energy in the red part of the electromagnetic spectrum, and one image that is recording the reflectance in the green part of the spectrum and in the near infrared part of the spectrum. So satellite data is actually then, in a multispectral sense, contains of many images, many different images covering the same area, but each have the reflectance in its specific wavelength band. Therefore, there are some formats, for example, BIL, which is then band interleaved by line. So it's one file, but all the 3, 4, 5 images are in the same file. So here it says that band are interleaved by line. So the first line reads the first channel, and the second line then carries information about the second image, and so on. So it's interleaved by line. It can also be interleaved by pixel, BIP file. Then we have one pixel value, and then the next pixel value contains the reflectance in the next band, wavelength band, and so on. Or it can be a BSQ file. And it could be also a composite file where we have actually the multiple bands are in the same file. They have been put together into a composite that holds the different multispectral bands then. And then we have the RGB possibility also, which we can say is a normal color image. It actually consists of 3 different images, and one providing the reflectance in the near, in the red part of the spectrum, the other image in the green part, and the third one in the blue part of the spectrum. And together they will form a color image called an RGB file. And GIS programs are designed to be able to read or at least import different raster formats, as there are so many different ones. So it has to be able to read and understand many different formats. Now, as I said before, a raster file needs georeferencing in order for the GIS program to know where the raster image is located on the Earth and to be able to place it correctly according to other geographic data that we have. So we have the satellite image. It has to fit, of course, where the other data are located in a certain projection, maybe, or something. So it needs some georeferencing. And if it doesn't have the same coordinate system as my other data, I will need to reproject either the other data to the same as the satellite data, or the other way, reproject the satellite data to be the same coordinate system as my other GIS data. And many formats are having in a separate file, the TIFF world file. We've talked about that already. And also the GeoTIFF file. Some formats have the georeferencing stored inside the image file. Sometimes we need to actually transform the geometry of the raster image or the satellite image into something else. Maybe we don't even know what the geometric is in the file, what projection or what coordinate system. It may just have plain coordinate systems according to columns and rows. And then we need to perform a geometric transformation. And by doing that, we find a set of control points that we can find both in the image, satellite image, and in maybe a map or a digital GIS layer, for instance, roads. If we can connect points in the satellite image to positions in the geo-corrected data, for instance, the roads, then we can transform the satellite image into the same system. And that's something we call geometric transformation. And that can be a map to a map. If we have a map without a projection, for instance, we can, and we have one map where we have a coordinate system, we can transform the unknown coordinate system to the map. That's a map to map transformation. For satellite data, we can do then an image to map transformation. So that would be then, we have a satellite image. It has no geocoding, but we have a map. It can be a digital map with the coordinate system, and then we find common points in these ones, and then we perform a transformation to get the coordinate system into the satellite data. And we can use an image to image transformation. That is often done when we have two satellite images and we want to fit them perfectly to each other. So we may find a house, in a small house in one satellite in the unknown coordinated satellite image, and we find the same house in the satellite image where we have a coordinate system, and then we can transform it so they have the same coordinate system. So geometric correction, that is called Geometric transformation is sometimes called geometric correction or georeferencing or rectification, registration. Could even be called rubber sheeting, because sometimes it has to be the transformation is like having a rubber sheet that you stretch out in some directions. So when you work with geometric transformation, you have to collect a set of ground control points. That means identifying cells in the image that contain some special feature and that you can position accurately or very accurately in a georeferenced map or image or something like that. And it's of course important that we find very, very distinct positions. For instance, a road crossing, we should be able to find in the satellite data and also in the vector data where we have the coordinates. A building corner, for instance, because this transformation needs to be as good as possible, of course. Otherwise, I introduce errors in my satellite data. So the GCP image coordinates in the raster, the column and row coordinate system, if it doesn't have a real world coordinate system, can then be transformed to georeference coordinates through a polynomial mathematical equation. And we will see how that looks in a little while. And then I collect GCPs. I check what the errors are when I in my mathematical transformation equation, and I then apply the equation to the entire image. All pixels will be transformed using the same equation. And then my root mean square error will, for the transformation, will provide an estimate of the error for the transformation. So we can see that here. We have here a satellite image that doesn't have any coordinate system. It's unknown. So it just have columns and rows. So all cells have a coordinate system in the image space only. What column it is and what row it is. And then here we have another image or a map or whatever where we have a coordinate space. It has coordinates. And if we link together then positions here with this one, we can find this geometric transformation between the GCPs. It's compared to the image transformation for the best fit using a polynomial equation. And then we have an error, of course, also always. But it's important, of course, to make that error as low as possible. So here we have the satellite image. We have that uncorrected one. And here we have a digital road vector layer. And we can now find points, ground control points in these, between these two data sources. And what could be a good, of course, we shouldn't take a car because the car doesn't stay where it is. We have to find very sharp places. Maybe the road corners are always good to put there. This one is not so good because can we really find this point? Here comes the road, and it crosses this one. But where in the raster data is that position actually? It should be over here. It has here. Here we have the GCP. It should be here, and this is then the residual, the error between the two coordinate systems. So we try to find corners or road connections, things like that, very sharp and defined places. So here we have a file with, in this case, 14 GCPs. We have the X source, which then would be the image space, and Y source, the Y coordinate in the image space. And here we have the coordinate system. So this one is actually going from one coordinate system to another. And here we have the residuals telling us how, if we use this transformation, what is the error of these ones. And I will look at this. I will add control points. I will check the residuals, and also the total RMS error for the transformation would be then 8.31. And in this case, it's in meters, both. So that would be, my satellite image would then be, using these points, would be 8 meters wrong as an average, of course. And we can see that this ground control point has a residual of 13.6 meters. So maybe if I have a couple of points with high, I can remove them, or maybe try to move it a little bit, see if I can fit it better, to reduce the residuals and get the lowest total RMS error. And then I will use a transformation equation to transform the image, and then it will actually get a coordinate system. The root mean square error is a measurement of goodness of fit of the control points, and it measures the deviation between the actual and the estimated position or location. And then it takes all of these. This is just the X for 1 point. And then if we summarize all the points, we will get a total RMS error. The transformations that we can do is then, if we have the original data, we can use an undefined transformation. We can use a second order polynomial or a third order polynomial. The higher polynomial I use, the more control points is required. And we can see in this table here that we have different transformation possibilities. We have an original grid. We can transform it congruent, but then we can only sort of flip it to one side. If we use a similarity, we add a scale, so it can be flipped, but also changed in the size. Affine will then produce a parallelism, and a projective one may be able to transform the raster image in this way, and a polynomial one will then be able to apply an ordered polynomial equation, and normally we don't go higher than third order polynomials, but it's possible, of course, to do more, to higher polynomials. Satellite data may also need to be corrected for sensor-related effects and scene-related effects. That's something that is called radiometric correction. This is required if the objective is to compare two images, for instance, and look at how reflectance have changed between two images, maybe taken 1 year apart. And it is, of course, very important if the images were taken by different sensors. Maybe I have one satellite image that was taken by the multispectral scanner Landsat MSS image, and the other one was taken by Landsat TM sensor, that then have slightly different sensors, and I need to correct for that difference in the sensors, or if they are just taken by different times. If one was taken in the springtime and one was taken in the summertime, I can also correct it for those things, for scene related effects then. And that is required if I need to compare them, do a ratio between them, or maybe stitch together many satellite images into a mosaic. And I'm sure maybe you've seen in Google Earth or something that satellite images looks different depending on what year they were acquired, or where in the season they were acquired. And trying to get that together as good as possible, that's how we correct for scene related effects. And one thing that we can do, often an absolute calibration is performed already at the receiving station, because they know the differences in the sensors, the detectors that actually measure the energy amounts. And so they are doing a correction going from raw DN to calibrated DN. So that's when we get the satellite data, it's already calibrated. But then we may need to calibrate for different detectors, or different bands, or different time variations. Now, sensor-related effects, that can be done by that's a relative calibration then. So we calculate, instead of the DM value, that is the value we have in the pixels from the satellite data, we calculate instead spectral radiance. So we get an L value in the pixels instead of the DN value. And then we need to know a little bit about the detector used by the sensor in the satellite. What's the minimum that it can actually measure, and what's the maximum, and what's the DN max? That's how many bits are used to spread the values between the minimum and maximum. So if we instead calculate the spectral radiance as an energy instead of DN, and we do that for the other satellite data as well, then I can compare at least the spectral radiance. I don't only compare different DN values in the satellite data. And this is sort of the equation to do that. You can look at that yourself. The DN max is then the maximum digital number depending on data type used. So if the data have been stored using 7-bit data, I have 127 levels, different levels that my L minus or L max minus L mean can be spread out in. If they used 8-bit data, I have 256 actually different values from 0 to 255. And some scene-related corrections are often required as well, because depending on the acquisition date of the satellite data, the incoming solar energy may be different. And and also the sun angle, where the sun is actually the angle to the sun. And that is something we should correct for as well. Atmospheric effects is also something. Maybe one day that it was a lot of disturbance in the atmosphere that affected the amount of energy that actually penetrated to the Earth and was then reflected up to the satellite and then measured up there. And we would also have some topographic effects depending on the slope and aspect of the topography. So a common method to correct for differences in sun angle and solar irradiance is to calculate at satellite reflectance instead of, so we go from DN values actually to radiance, and then we now go to at satellite reflectance. So we normalize differences and normalize the differences in the reflectances measured by the satellite. And this is then related to variations in incoming solar irradiance and sun angle. And we know that the sun, the Earth evolves around the sun, not in a circular mode, but in a more elliptic mode. In some parts, the Earth is further away from the sun compared to other positions during a year. And the mean distance in astronomical units, which is then about 149.6 multiplied by 10 powered by 6 kilometers, quite a far distance. But in some seasons, this distance is closer or longer. And that should be corrected for if we want to calculate at satellite reflectance. And also the the sun angle. Here we see the sun angle, but we want to calculate it to solar zenith angle, as if the sun was in zenith at all times. And the solar zenith angle is then 90 minus the sun elevation. So this is what we normally see from the horizon, the solar angle up to the sun. But we want to go all the way to what's the amount of sun, if it's solar energy, if it was in zenith when the image was taken. So here's the formula to correct for the distance, the solar Earth distance. And here we have the radiance, the spectral radiance that we have calculated from the DN values. And then we have the E, which is the mean solar irradiance, the average solar energy being put out. And there we have the solar zenith angle. And this will give us a unitless effective at satellite reflectance. So now we have corrected for, firstly, we recalculated DN values into radiance, spectral radiance. And now we take the spectral radiance and recalculate it to at satellite reflectance. And if we do that for all our different data, we have at least corrected for as much as we can do in physical terms. Then we have the atmosphere left actually to compensate for. And let's have a look at the atmospheric effects. What is actually affecting the satellite image? Up here we have a satellite platform with a sensor that actually measures reflectance or energy, reflected energy from the surface. But as we see, the sun is shining here and it hits the atmosphere. And here are scatterings. Here, energy is lost. Energy is scattered from different particles. And so what we actually measure in the satellite is here we get a value of 53. We can say that that's DN values, digital number values. But actually only 45 of those have been in touch with the object on the ground. So that's related to target properties. But then we have added 8 is just based on the atmosphere. And that can then be different from different acquisitions. And it's this part that we would like to correct for. So we only have the target properties when we want to do when we want to compare to satellite images, for instance. The way to do that is we can use a physical model that actually calculates the atmospheric transmission at that point and the atmospheric background radiance for a certain atmospheric conditions. That will need to be on the same date as and maybe even the time of day. But it's possible if we can get that information. A simpler way that remote sensing technicians use is just to correct it for objects with known reflectance. So, for instance, if I have a deep and clear lake in my satellite image, that should be very, very dark. Because all the radiation is absorbed by water. So it should almost be 0 in the DN value. And I can look at the difference. If I have find the lake and it's the same, it has the same depth and should have the same temperature and things like that, actually. I can see the change of the pixel values. If the pixel values are slightly higher in one satellite image compared to the other one, we can think that the additional pixel values are related to haze or atmospheric properties. And that means I can actually reduce that difference from the whole image. So to take away the change, so this deep clear lake will have the same pixel value between the two images. I can, of course, also, if I have possibility, measure the albedo or the reflectance at certain positions in my satellite data at the same time as the image is acquired, and see what actually is coming out or reflected on the ground, and then I can correct my satellite images based on this. And resampling is another thing we need to do sometimes with satellite data. It's a process to fill a picture with a new value after the pixel have been shifted its location. Because of a geometric transformation, for instance, a reprojection of the satellite data, or a change of pixel size. Then we can understand if we reproject, the pixel that used to be in a position will not be there anymore. It will have slightly moved. It can be tilted, or it may have changed. So and then maybe the cell value that is there from the start, it shouldn't be the same as in the new pixel location. So there are different methods to determine how the new pixel should get its value. And there are normally three different types that we can use. We have the nearest neighbor. So that would mean if this is the new pixel position, it will get the value from the closest pixel that is close to it. This is a good way. It's a quick way for the GIS program to use, and it doesn't change the values. So the values are still the same. It just takes the new value based on the closest pixel. And this is good when values need to be preserved, or when, for instance, pixel values are categories. If we have land use classes, for instance, it makes no sense to if this pixel was forest, for instance, this pixel will be forest as well. Then it will have the same coding. The other way is to have a bilinear interpolation to determine the new pixel value. So the four closest pixel from the input will be creating the new value for the new pixel, and it's a distance weighted average interpolation. So it will be recalculated. So this one, based on the distance and the values here, will be, it can be maybe say that it's, this one is 1 and this one is 3. So it may be 1.2 instead, or 1.3 instead. These ones are further away, so they don't have so much effect. It's 1 and 2 that will have effect. This is good when averaging, when we need a new representation. For instance, if we have reflectance or radiance measured as we have in a satellite image, it's a way to actually get a representation of the new location of the pixel based on the four closest pixels around it. And then we have cubic convolution that instead uses 16 input pixels and not 4 as the above. And it will try to fit a polynomial equation to interpolate the new pixel value. It will take more computer power to do every pixel value, and also produce a quite smoothed surface as when the next pixel value is to be calculated, it will use many of those values as it used in the pixel before. Okay, so I hope this was not too technical, but that you now understand that we sometimes we need to correct satellite data. It maybe we need a geometric transformation. Maybe we need to correct for the radiometry, which then are the sensor corrections, or maybe the scene sensors, that we have different sun angles and incoming solar irradiance. And then sometimes we need also to determine how to resample pixels in a satellite image. And then we have the nearest neighbor, we have the bilinear interpolation technique, or we have the cubic convolution to choose how we want the resampling to be done. Okay, thank you. Good luck.